Just a couple announcements before we get started. Immediately after this talk, at 5 o'clock in the chill out room, the demo party, for those of you who are into demo scene or any of the people that want to see what it's all about, that gets started at 5 o'clock in the chill out room. And then at 8 o'clock tonight, here in the ballroom is dinner and the party starts. Okay? So, please give a hand for z0rro.
Yeah, all right. Cool. So this talk is how containers contain. It's kind of an overview of container technology's underlying technology. So it's pretty high level, but a little technical at the same time. I'm not going too much into the uber crazy security lockdown parts of everything. It's more so the bits beneath containers and how they work. This covers things like Docker, LXC, most every type of framework that exists on Linux for containers. So what this talks about, who this talks for, again, it's not crazy. I'm not going to get into SE Linux, AppArmor, JR Security, SecComp, anything really cool. I do blue teaming stuff. This is more blue teaming stuff. It's not sexy red teaming stuff. This is me. You can find me on the Twitters and on IRC. So what is a container? Unfortunately, I don't have these slides in front of me, so I'm going to be somewhat reading these as I go. So basically, containers create an isolated environment for processes to run. They all share the same kernel in that system, so they're running on the same operating system, same computer, as most everyone knows, but they are contained. They are kind of segregated in their own world to an extent, usually between container to container. That you're not actually virtualizing the hardware at any point in time, nor are you virtualizing another operating system. So you've got one shared kernel for all containers across the board. A brief overview of what that looks like on your left, virtual machines. You've got your services, your operating system, your virtualized hardware, your actual host operating system, and then your bare metal on the bottom. The same thing on the container side, but you've got just your services, your host operating system, and then your bare metal. So there is no virtualized server, and technically there isn't really a virtualized operating system. That said, you can run different file systems, different distros if you'd like. You're still going to have the same kernel, but you can have a Debian host with a Arch container if you would like. So red was clearly a bad choice, but these are basically the underlying technologies used in container frameworks. Pivot root and chroot. I'm going to just cover chroot because pivot root is a little magical to me still, but we'll go through an example of each one of these. Chroot is usually used just to contain a file structure or give the appearance of a contained file structure. Kernel namespaces are what give you the actual segmentation of processes and restrictions of views to what resources these processes can see. We'll get more into what that looks like. And then C groups. C groups are usually used for restrictions on resources. They can also be used for accounting purposes. So if you want to see over time how much memory has been used by an application or how many CPU cycles have been used by a certain container or just a single application, you can do so. Lastly is kernel capabilities. The kernel capabilities is kind of just a fine-grained control. So instead of doing set UID, you can now go in and say this group of processes or just this process can do this one special capability. So what do containers look like? Kind of hard to see, but this is from the host operating system. You can see that this red section here is the actual container sitting inside of the host or on top of the host. So from the host view, these are all just processes that are running. If you were inside this container, however, you would have a very limited view outside of this container. So what does that mean? This means that if you mod probe something in a container, you mod probe something in real life. So that means that you have to kind of go out of your way to really restrict what access you're giving to these containers as you're doing it. chroot, just going to go through it very quickly. I'm sure everyone here probably knows what it is and doesn't want to hear about it, but it changes the apparent root directory for the processes or a group of processes. They're restricted to that root. It now becomes their top of their file system. They can't see beyond that. Generally, we use the chroot command, which is a wrapper to create these. And again, most container frameworks actually use pivot root and a combination of chroot as well. It seems pivot root will actually change the entirety of the root file system, and then chroot creates the chroot environment inside of that. But I haven't done much with pivot root, just chroot. So a quick overview of how to do a chroot. Don't do a chroot like this, but very quickly, the first thing is if you want to chroot a single process, you need to ensure that everything that process needs is in the folder you're going to be chrooting. So if we find a file like find, we find all the dependencies that it needs, we grab all those dependencies and we put them in a directory called test. We can then bring a file structure over that emulates the root file system with all of these libraries, and once that's done, we can actually chroot that directory and run our command, and you'll see the output there is the find command listing all the files it has in its file system, and as you can see, it's just what we've moved into that chroot container there. The next one is kernel namespaces. Kernel namespaces originally came out of Plan 9. It's a functionality of the Linux kernel, as I said before, that basically lets you isolate many things. It lets you isolate a wide variety of different things, which we'll go into in depth in a moment. You can isolate all the way from like processes, users, IPC, file systems, network access. And there's always new ones coming out. When I was doing this research, I found that it was kind of hard to keep up with. I always had to find the latest and greatest version of, I think most of the work I did was on Debian, but in order to get all the latest namespaces and in order to get all the latest C groups, which I'll get into, they're changing constantly. Right now, there's a proposal to add a time and a syslog namespace, but as it stands right now, the most common namespaces are these ones that are listed here. I won't go into all of them, but for example, you can restrict what mount points are visible to the container. You can restrict what processes are visible to the container. You can give a container its entire own network stack. You can give it its own IPC. You can limit its users as well. And the user namespace is something that was added very recently, and it's actually really important when it comes to security. I'll talk about that in a moment. So how do you control these namespaces? There is a API, which is really just 3 syscalls: clone, setns, and unshare. Setns will let you set a namespace. Unshare allows you to create a new namespace for a process that you call, and I'll show you an example of that command line in a minute. The namespaces themselves, you can usually see all of the namespaces for a process. If you go into proc, PID, and then the namespace directory, all of the namespaces are there, and if you look at any of those files, it'll have the actual namespace identifier inside of them. So if we wanted to view namespaces of 2 different processes that are in different namespaces, again, this is the container running on the host OS. We're just going to grab the PID for both systemd instances, the one for the actual operating system that we're running, and then the one for the container. If we go in and we take a look at the actual PIDs and the namespace directories, you can see that they share similar but not all namespaces. So, oops, sorry. So in this case, you can see that they're in the same cgroup namespace, the same network namespace, the same user namespace, but inter-process communication, mount points, PIDs, and I believe host names are all contained within the container. And this is a very easy way or somewhat easy way to view the existing namespaces for a process. There's a wrapper called unshare. With unshare, you can basically call a process, and when you call that process, you can say, hey, I want to give this process its own network namespace. I want to give this process its own PID namespace. And instantly that process will be spawned, and a namespace will be created for it, and it will be limited and restricted to those resources. You can do any of the ones there on the bottom. Again, this list is always growing. There's always new namespaces coming out. It's kind of a crazy time right now with this tech. So what does this look like? In this case, I did unshare PID, mount proc fork, and then I ran top. You can see here, these are that first one is PID1, this other one is the proc PID. You can see that the mount namespace and the PID namespace differ as they should, because that's what we've told it to do. And then if we actually run top, you'll see that it's the only thing all by itself, no other processes there, and that was the unshare command that we ran originally to do that. And it was as easy as that unshare PID, mount proc, fork, and then the actual command itself. So that's basically namespaces. So user namespaces came out, I want to say maybe a year and a half ago, maybe 2 years, but user namespaces actually let you create a simulated UID sets. So inside of your containers when you start them up, or single process when you start it up, it will actually shift the UIDs. The old issue used to be that if you were root in a container and you broke out of the container, you're now root in the host. So with user namespaces, if you're inside of the container, the root user appears to itself to be running as root. But if you actually look from the outside, if you look from the host, the PIDs are actually, the UIDs and GIDs are actually shifted. So if you were to break out and get onto that system, you have a UID that doesn't exist. Therefore, you have no access to any resources on that system whatsoever. And this was kind of a big thing. And a lot of people were kind of slow to adopt this. When you start talking about LXC versus Docker versus Rocket versus NSpawn versus all the systems that are out there, one of some of the earlier adopters, I think, were NSpawn. I think by default, Docker will do this now, but it's a newer thing, and it's very, very handy, and it helps with security. But like I said, since these are new and they're always coming out, there's lag in their implementation on when the frameworks actually pick them up. But just to wrap it up, namespaces is what's used to actually do the segregation of these processes or process, and there's userland tools to allow you to configure that. So C groups is the next one. C groups is basically resource limiting. The resource limiting is pretty fancy. You can do quite a bit with it. I'll get into what resources can be limited. There's also the ability to freeze a group of processes all at the same time, or a single process all at the same time, which doesn't really make sense for a single process. But to control the C groups, they give you a pseudo file system, kind of like procfs, where you go in and you can actually set bits in the pseudo file system in order to control your different C groups. And I'll walk through kind of handling C groups and making a C group and adding something to that C group. So these are the more popular C group subsystems. Again, there are more than this, and there will be more that will probably continuously come out. But CPU is a very popular one. It's not based on percentage, it's based on shares. You can guarantee certain processes or groups of processes more shares, so that when the system load gets bogged down, certain processes will always have access to CPU cycles when others won't be prioritized. It's kind of like traffic shaping, but for CPU. Good example of this is if you're an admin and you want to always be able to get into your box, even if it's like getting DDoSed, or if someone's doing a denial of service on a service, you can actually set your SSH daemon to have a higher value here, and your SSH daemon will take precedence over everything else on that system, so you can always SSH into your box no matter what's going on, and then try to handle the situation from there. That's a very popular use of it. CPU set allows you to actually bind a set of processes to a specific CPU. Memory is used to limit the amount of memory, the amount of swap that can be used. You can also use it for accounting as well. Disks, devices, again, freezing, and PIDs. So these are all different subsystems, and like I said, there'll be many more probably in the near future. So how do you control these things? A lot of the command line tools just modify sysfs C group, and we'll go in there and play in a second so you can see what that looks like. But there's a lot of userland tools that are probably better and a lot prettier than going in and modifying these files. But long story short, a C group is created by creating a specific directory in the appropriate subdirectory of the C group file system. So when you go into the C group file system, you'll have, I think it's sysfs C group, and then memory, CPU, all of your subsystems are there. And all you do is you just create a new folder in one of those directories. So if you go into memory and you create a new folder called demo, all of a sudden you've created a new memory C group called demo, and then you can add tasks or add PIDs into that C group, and then you can set restrictions on that C group. And now every task that's added to that C group, every process that's in that C group has those restrictions applied to it. So yeah, that's that. So how do we view C groups? Again, it's a pseudo file system. So if you run mount, you'll see all of the current C groups that are currently mounted. And if you go into your processes and you just take a look at the actual C group file under proc PID and then C group, it'll list out all of the C groups that your process is a part of. Obviously, it's blank if it's not a part of any of them. So this is kind of what I was talking about a minute ago. This is an example of the CPU C group. In this case, I created a folder called test1. Now I have a C group, a CPU C group called test1. For me to go in and to limit the CPU usage, or to limit the quotas, to limit the shares, to limit whatever, I can go in and change any of these values. To add tasks to this C group, to add PIDs to this C group, all you do is echo the PID into the tasks file. So that bottom there is you just grab your PID, take your PID, echo it right into tasks, and now that process belongs to that C group that you've just created. So there's always a task. All of these files get auto-populated. So in this case, when I created the test1 directory, all of these files were automatically created for me, and then I can obviously go in and set these values. But lastly, the tasks file is just as easy as just throwing PIDs in there, and then they become part of the C group. So C group demo, how can we use C groups without using the entire container framework for resource restriction? This is kind of a lame demo, but it was an easy way, I thought, to demonstrate the usability of C groups. And in this case, I'm limiting the memory usage of Nginx. So the first thing I do is I create a new memory C group called demo. I then grab my PID. All children inherit the C groups from their parents. So if you're in Bash and you run something, that by default will inherit the C groups that have been set for that Bash session, which is what I'm doing here. So because I'm getting my PID for my current Bash terminal, which is the 14575. I'm then adding that into my new demo memory group under the tasks file, or into the tasks file. And then after that, I'm limiting the total amount of memory that's allowed to be used for this C group. In this case, the C group only has that one PID, but I'm limiting that to 2900K and just adding it to the memory limit in bytes file. Once that's done, I start up Nginx and just leave it running. And then once that's running, I just do a curl request to my local host on 9090 where it's bound, and I get that test response, which is just an index file. But then the next thing I do is on that same Nginx listener, I request 8,176 A's, and the server just shuts off. The reason it kills it is because it exceeded the maximum amount of memory. Realistically, in different environments, there are other settings you can set. There are settings that don't hard kill it. There are settings that will try to re-nice things. But this is kind of just an in-your-face demo of what you can do. Obviously, you don't want your processes to just die. But so kernel capabilities. Kernel capabilities are, like I said, kind of fine-grained control over root access, root abilities. They divide system access into different groups. When a process is created, it's given a set of capabilities from the kernel. It's what it can and can't do as far as root capabilities go. Again, if any child that comes from that will inherit the capabilities of its parent. There are a lot of kernel capabilities. So you can go into a process and you can say, hey, I want this process to only be able to mount disks, or I want this to as a root user, or I only want them to be able to chown only, or chroot, or talk to syslog. So there's quite a few. What started happening though is as these were being developed, they started grouping different writes into single groups or single capabilities. So things like cap sysadmin let you do a lot of things. I think also the cap net admin will let you do far more than you might expect. And when these systems were first coming out, Docker and LXC, they've all had a history of escapes. I don't know if anyone remembers the inode brute forcing with Docker, but that was an issue with the kernel capability where you assign these capabilities and you think, oh, well, it should be fine. This is just to mount disks. But then you realize, well, no, actually, you can do really crazy crap with it that you never expected, and you can break out of the container because this capability lets you do it in some obscure way. So they've been around for a while, but they're still kind of unvetted, and they're still kind of dangerous. So you kind of have to add capabilities carefully and really read up on what they do, and even then, you don't know truly unless you're going through the source code as far as what power you're granting to these processes. So you never ever want to grant cap sysadmin, and that was granted for some time on some by default. I think, honestly, Docker probably does the best job right now with the default set of capabilities. LXC is a little heavy-handed, but yeah, there's quite a few there. And again, these allow fine-grained control of root access. So how do you control these and how do they work? Each process has a set of bitmaps. Capabilities are implemented as bits into these bitmaps. The bitmaps are referred to when the process goes to do an action. So you can use, for userland stuff, setCap can be used to grant a capability, and getCap can be used to read the existing capabilities from file so capability sets, there's effective, permitted, and inheritable. Effective are what that process or group of processes currently has. Permitted is what it is allowed to assume it can actually get it, and inheritable is what it got from its parent. Again, these are all different bitmaps as shown there under the first section. So to view kernel capabilities, you just go in and looks like in this case, let's see. You can use the getcap command. There's a variety of ways. I think getcap was the best one I found. In this case, I'm looking at the ping binary, which of course has capnet raw, effective and permissive. You can remove this capability. You can add other capabilities. If you do a pscap, the pscap command will show you all the capabilities for everything that's running right now. This list was huge, so I kind of trimmed it back. But for viewing capabilities, getcap is probably the best option. So a demo with the capabilities. In this case, I'm using Nginx again. Nginx wants to bind to port 80 by default. Obviously, you can't. It's a privileged port. So if we go in and we add the capnet bind service capability to just the Nginx binary, we're going to use setcap. So the first command is getcap, show me what you got. It doesn't have anything. So we do setcap, and we give it the capability for the capnet bind service just to the Nginx binary. Then when we call getcap again, we see that it's listed as having it. If we actually execute Nginx as a non-privileged user, it can now bind to port 80 because it has that the ability to do so. But it just has that single kernel capability, so it can't do anything else special other than bind to privileged ports. And it's nice because you're not having to initialize as root and then drop your privileges down. You're also not having to do wacky set UID stuff. So again, just an example of the fine-grained control that you can get with the capabilities. So I'm almost actually close to done. This is pretty quick, but instant container. So I don't know. I think most people have probably used Docker. Docker, LXC are kind of the most popular. LXC has been around for a very, very long time. Docker came and kind of piggybacked off of a lot of the work LXC has done. I am not a fan of systemd, but I am a fan of systemd nspawn. Nspawn, it seems to be originally created for developers. The man file actually says don't use this in production ever. Rocket, however, decided they wanted to use nspawn, so they convinced them to remove that from their docs and kind of use some more secure default settings. But the nice thing about nspawn, I think anyways, compared to things like LXC, is it's easy to use. Docker, to me, is pretty bloated. If you're just kind of playing around with this stuff and you just want to throw something in a container, to to deal with the behemoth that is Docker is probably overkill 90% of the time. So in this demo here, I'm using nspawn. The first thing I'm doing is I'm just creating a Ubuntu 1 folder. I'm using deb bootstrap to pull down Ubuntu image into that folder. And then I'm using systemd nspawn. Oops. I think I've got. Yeah. So systemd nspawn-d, and then the folder name where your file system sits will basically just drop you right into it as if you were booting into single user mode. The reason we do this first is because we have to set the password. You could probably go in and you can do it a few ways, but this is one of the quickest ways to do it. Once you've set the password as shown there, you can then exit the container, now shut down, and then you can start the container back up. This time you do the tac-d, but you add tac-b for boot, and it will do a full system boot. So really all I've done is just made a directory, put a file system in it, changed the password, and then started it up. Once that's up and running, that's what it looks like. So full-blown container, you can do just about everything else. It's persistent storage. The storage resides inside of that folder. You can zip it, move it around, tear it down. nspawn also has, again, it's kind of continuously growing as these things do, but if you want to use nspawn, one of the nice things is it works well with systemd service management. So there's a folder called var-lib machines, and if I actually had just created that Ubuntu folder in var-lib machines, I can now use systemd's service control to manage my containers. I can say, systemctl enable Ubuntu 1, and now on boot, Ubuntu 1 will come up. I can stop, I can restart it. Also, all of the systemd utilities have the ability for you to, I think it's tac-m, and then put in your container name, but if you want to do journal D, you can read your journals from your container from the host just by specifying the container name. If you want to stop and start services from the host, you just, I should know the switch, but you throw a switch in there, I forget what it is, and then your container name, and now you're starting and stopping services in these containers from the host. They also have machine.ctl, which allows you to do management in a similar fashion. But again, I like nspawn just because it's quick and it's dirty and it's easy. There are more persistent methods than what I've shown to actually use it if you want to use it. I don't know if I would claim that it's production ready by any means. By default, unless you go in there and start picking apart the kernel capabilities and the namespace configuration, it does not default to a secure configuration. So if you have a container system that is not using user namespaces, they're doing it wrong. So you should be checking that and ensuring that your container framework is indeed using user namespaces. And then take a look at the capabilities once you start these containers up. If you start a container up and you see that it's got way more capabilities than it needs, a lot of these frameworks allow you to go in and modify templates to remove these capabilities. And you can do it on the fly, but obviously that doesn't really scale. And yeah. So I didn't talk about SE Linux. I didn't talk about seccomp, AppArmor, or GR security. In comparison, in tandem with all these other things that I had gone through, usually you don't run any of these without one of these hinged onto it. I won't go through all these because they're all probably a talk in themselves, but definitely take a look into them. Seccomp is one of the more popular ones that's used, but definitely worth looking into. Seccomp, from my understanding, allows you to profile syscalls, and then you can tell a group of processes or a container, hey, you can only make these syscalls, so you can kind of profile it over time, if I'm understanding it correctly. I'd actually never used it. And then you can actually say, okay, well, you can only use these syscalls when you're running and operating. So a lot of resources out there. I'll have my slides up somewhere, but a lot of man pages, and GC562 is awesome. That's all I got. Questions? No? Awesome. Yay, containers.